Hello, Professor Cormen. How are you?
Hi, good. How are you?
I am fine. Thanks for being here.
Okay. Is my sound okay?
Yeah, can you hear me well as well?
Yeah, I hear you just fine.
All right. I'm glad we have the chance to speak today because it's the 23rd of June, namely Alan Turing's birthday. And we all know about the historical impact of his work on mathematical logic. But relevant for us is that he made precise the notion of an algorithm, and he wrote the foremost algorithm book, The Introduction to Algorithms. So can you please tell us more about the process of writing the Bible of algorithms and the impact it has had on your life?
Oh boy. So the process is, I was a graduate student at MIT in the theory of computation group. I was just starting my third year of the PhD program. I had an NSF fellowship that was good for 3 years, but they did not have to be three consecutive years. I'd used it for my first two, and at MIT, you have to get a master's along the way to the PhD. So the first 2 years were spent getting my master's. And the advice I got from other grad students was take the third year off from the fellowship because you're burned out from doing your master's. So why waste that fellowship year when you're not going to be very productive? So I took that advice, which meant I had to either be a TA or an RA. So I was a TA. I was a TA for the MIT course known as 6046, because at MIT everything is numbered. And that was the undergraduate algorithms course and was being taught by my advisor, Charles Leiserson, my research advisor. I was a course development TA. I was an extra TA. So I had very little interaction with the students. I would meet with the students every third week, I think, and do a section. But the other TA was more student focused. My job was to come to the lectures, have Charles Leiserson's handwritten notes in front of me, and then write them up in LaTeX in prose form for the next class, which was either a Tuesday or a Thursday. So I either had 2 or 5 days. So that's what I did. At the end of the term, Charles said to me that I did a really nice job, and how about we turn this into some sort of book? And the idea he had in mind was not a textbook. It was something like a lecture notes in computer science book. For example, Dexter Cozen has one of lecture notes in computer science, published by Springer Verlag. So that sounded good. I'm in just my third year of grad school and write a book. Sure. So we set off to do that. And over the next few months, two things happened to change the scope of the project. One was Ron Rivest in the spring. So the course I TA'd, I should say, was in the fall of 1986. In the spring of 87, Ron Rivest was teaching the graduate version of the course, and he started editing these notes. So that got Rivest into the project. And then somehow, and I still don't know how it happened, it turned into a textbook rather than just lecture notes. And little did I realize that the amount of effort of lecture notes compared with a textbook was probably about a factor of five. The things you have to do in a textbook compared with just a book of lecture notes are about 5 times the effort. Things like consistent terminology, problems in exercises, illustrations, and index, all sorts of things. And of course, just length. We were writing and writing and writing, and around early 1990, we decided to stop writing because the book had already become over 1,000 pages. We figured that was enough. So we finished writing in, I think it was March of 1990, and then the book actually came out in June of 1990. So that was the first edition. So that was the one known as CLR, Cormen,
Right.
Lyserson, and Rivest. And it was really just the right book at the right time. There were already algorithms textbooks out there. I grew up on the Aho, Hopcroft, and Ullman book, The Design and Analysis of Computer Algorithms. That came out right after my freshman year of college. And I immediately got a copy and really went into it. There were other algorithms books that were out by 1990, ones by Horowitz and Sani, Broussard and Bratley. Um, uh, Sarah Boz had a book out. So there were already some books, but ours was bigger. ours had all this coverage, and I guess people liked how we did it as well. So it quickly became very popular among university faculty. They started adopting it. And I think within a year or two, we had about 200 universities worldwide using the book.
Yeah.
So yeah, so that was the origin story of the book. It came out while I was in grad school. I didn't finish my PhD until 2 years after the book came out.
I mean, I took two algorithms classes at Oxford, and I used your book heavily in the process. And correct me if I'm wrong, but you're currently working on a fourth edition, right? What should
That's right.
what should we expect from that?
Yeah. So just to back up a bit, we put out a
Okay.
second edition in 2001, and that's when we added Cliff Stein as the fourth author. So I knew Cliff quite well. We had actually been office mates at MIT. When he got to MIT, they put him in an office with me. So I knew him quite well. And he and I started at Dartmouth together in 1992. We decided that we needed to add a fourth author for the second edition just because of how much time everybody would have to put in. And I joke about, well, in theoretical computer science, you list authors alphabetically. So we needed somebody who came after CLNR, and I walked down the hall and there's Cliff Stein. So we added him, and that was really good. He and I worked very well together. In fact, I'm just going to, again, tell you a story about the second edition.
Yeah, sure.
And this is a story about how you can get caught up in your own craziness. And I think this is a valuable lesson for all authors. And I remember reading Jeff Ullman, who's, of course, a terrific computer science author, talking about getting caught up in your own craziness. And Cliff and I have a great example of that. We were writing a new chapter for the second edition, the one on probability, where we had randomized algorithms, new chapter. And we worked on it for about 7 weeks, as I recall, where Cliff would take it Monday through Friday, then hand it off to me for the weekend. I'd work on it for the weekend, hand it back to him Monday morning. And we did that for 7 weeks in a row. Then, excuse me, then we sent it off to our copy editor, Julie Sussman. So Julie is just terrific. She's a great technical copy editor, but she's also really good with language. And we sent it to Julie, and we knew it would come back with not a mark on it. We knew it was perfect. We get it back. It is covered in ink. And Julie uses 4 different colors depending on what type of comment she's making. Red for this is an error you must fix, green for a question, things like that. It comes back covered in ink. And Cliff and I look at each other and we're saying, what the, what were we thinking when we wrote this? And just as an example of how off track we got, there's only one thing that you can take the probability of, and that is an event. We were taking probabilities of things that were not events. So it's just amazing how crazy you can be when you're just writing. So yeah, so we added Cliff for the second edition that came out in 2001. We did the third edition in 2009 that came out then, and now we are working on a fourth edition. We're still working on it. I can't give you an exact date when it will be out. But the fourth edition, my favorite aspect of the fourth edition is it's going to be in color. For the last 3 editions, we've been pleading with MIT Press, can we please have color? Can we please have color? And for the fourth edition, they finally consented to color. And this is another case of be careful what you ask for, because I actually produced all the figures for all the editions of the book. And I did not realize how much effort it was going to take to colorize all 250 plus figures for this book. And I'm still working on it. Cliff is actually a little bit colorblind, and he's remarked that there are some figures where he's having a little trouble with the colors. So I'm having to go and ooch the colors a little bit so that at least my co-author can see the figures.
I mean, I am colorblind as well, so I hope I will be able to read it.
Okay. Well, we made sure that no figure has red and green because that's the most common type of color blindness.
Yeah.
There are other types, if someone is just monochromatic, there's not much we can do about that. But we made sure that no figure has red and green. So, yeah. And then there are, of course, other changes that we're making for the fourth edition. I'm doing a lot of rewriting just to try to make things clearer where I can. I'm putting in intuition. There are a few places where I've either added a section or rewritten a section to add intuition. There are chapters that we're cutting because, from what we can tell, people don't really use them. In fact, one of the chapters that we're cutting is one that we just put into the third edition, the chapter on Van Emdenbosch trees. So we're taking that out. But anything we take out will be online. So it's not like it disappears from the world forever, but it just won't be in the printed book. But we are adding some new material. We're preparing a chapter. I think right now we're calling it Algorithms for AI, and it's going to have things like gradient descent and clustering. We've been asked by many people for a chapter on machine learning, but we just feel like it's a little too much. There's a little too much of machine learning to actually make a cogent, coherent chapter on it. It would just be too much. And frankly, we have a page budget, and we would blow the page budget. So if you look at the third edition, you'll notice that the last page of the index is 1,292. And there are 20 pages of front matter, making the total page count 1,312. Now, when we signed a contract for the third edition, it specified a page limit. Guess what that page limit is?
Precisely
1,312.
Yeah.
So we made the page limit exactly, and we have the same page limit for the fourth edition. So we really do have to be mindful of the page budget. So that limits what we can put in, and also says why we have to take things out.
Right. This book, even though you told me you didn't write it with this purpose in mind, is the standard reference for competitive programmers. So a lot of people might be still in school, and I'm wondering what your thoughts are on the relationship between competitive programming, academic computer science, and software engineering in the workplace.
Yeah, so I know I've answered this on Quora. So competitive programming, it's not something that interests me personally. When I write code, I'm not trying to write code to show that I'm better or faster than anybody else. I'm trying to write code to solve a problem, or maybe to actually ensure that an algorithm in our book is correct. Starting with the third edition, anything new that I wrote up, I implemented just to make sure I got it right. And actually, I found several bugs that way. So I'm not interested in competitive programming for myself. That said, if other people want to do competitive programming, great. There's nothing wrong with that. And in fact, I like seeing people be creative. So if they want to be creative in their competitive programming, that's terrific. This is why I used to watch cooking shows. It's not like I could eat the food that they were making, but I just liked seeing people being creative in whatever manner. As far as how competitive programming dovetails with computer science education and software engineering, yeah, I don't know. And that's really because I haven't done competitive programming myself, so I can't really say what effect I've felt from it.
And I guess because of this heavy CLRS editing that you've been done lately, you have a lot of algorithms that are still fresh in your mind. So in my very first episode of this series, I talked with logician Joel David Hampkins, and I asked him what does he think of the topic of mathematical beauty. And now I want to ask you, what do you think makes an algorithm beautiful? And perhaps you might have an example.
What makes an algorithm beautiful to me is the simplicity behind its design, which doesn't necessarily mean simplicity of its analysis. So I'll give you a couple of examples of algorithms that I just really like.
Sure.
One of them is the Bellman-Ford algorithm for shortest paths in a directed graph. And that is the algorithm that allows for negative weight edges as long as you don't have a negative weight cycle. And the algorithm is incredibly simple. It says, go through all the edges and relax each edge. And do that card v minus 1 times. In other words, if you have card v, in other words, let's say you have n vertices, n minus 1 times, go through all the edges and relax every edge. It's really simple. I mean, you know, the pseudocode, the real code are incredibly simple. And the reasoning behind it is really simple as well once you have the appropriate understanding of what it means to relax edges in a graph. So I really like that one, and you know, it allows you to do shortest paths on a graph with negative weight edges. You can, you know, use this to do things like find arbitrage situations. The other one that I was thinking of is the disjoint set forest algorithm for disjoint sets. So this is the one where you just maintain a forest of sets. So each set is a tree where all you need is a parent pointer for each vertex. And there are two heuristics that really help. One is union by rank and the other is path compression. The pseudocode, and in fact the real code, is incredibly simple. For the three operations you need, making a set, finding what set an item is in, and uniting two sets, the pseudocode altogether is like a dozen lines for all three operations. It's amazingly simple. And converting the pseudocode to real code would not add many lines. I mean, it's amazingly simple. And the running time is so weird. It's not quite linear. It's off from linear by this inverse of Ackermann's function, which is incredibly slow growing. Like it's at most 5 for up to the number of atomic particles in the observable universe. But mathematically, it's not a constant. For all practical purposes, it's a constant, but mathematically it's not. And the analysis is really hairy. It's by far the most complicated thing in our book.
All right.
But you don't have to understand the analysis to use the algorithm, but the analysis is really, really complicated. It was Bob Tarjan who came up with the analysis. And I mean, I can't imagine having come up with that.
And speaking of running times and efficiency, let's take a detour into one of the most famous problems of computational complexity and algorithms, namely the P equals NP problem. I mean, we know that no one managed so far to prove or disprove this claim, but what are your thoughts on the matter? Where do you stand?
So I'm in the radical fringe that thinks that P equals NP.
Really?
Yeah. Like I say, the radical fringe. I'm in good company. I'm told that Don Knuth feels the same way. And then, when I'm asked why, well, I don't have any concrete reasons. Nobody has any concrete reasons for why they feel one way or another. And of course, this might be one of those things that we'll never know, right? It might not be provable at all. Who knows? Here's why I think it. There are problems in P that are just so close to NP complete problems that it's just so frustrating to me that the NP complete problems are not polynomial time solvable. 2-sat versus 3-sat, shortest path versus longest path, Euler cycle versus Hamiltonian cycle, things like that. They're just so similar that it feels like there ought to be a way to bridge that gap. Now, maybe this is me just being stupid and not realizing there's a difference between 2 and 3, and there's an important number between them, like E, and that for some reason it makes some fundamental difference in the world. I don't know, but this is my feeling. And then I also have this feeling that whenever this is solved, it's going to be by someone that we did not expect to solve it. It's not going to be by somebody who's studied the problem for 50 years. It's going to be by a college sophomore.
Why? Because it requires a radically different mindset than what we've been trying so far?
Yeah, exactly, right? If you've been studying the problem for 50 years, you're just probably revisiting the same turf over and over. It's very easy to get caught in a rut of a mindset. Whereas if somebody comes in and just thinks completely different, then they might figure it out. So look, would I bet anything on my being right? No, I would not bet anything on my being right.
Do you think there's any potential chance for this problem to suffer a similar fate to what Cantor's continuum hypothesis went through, namely to show that it is undecidable within our contemporary mathematics?
Yeah, I think it's entirely possible. I just don't know. There's just so much that we don't know about this problem, and that we've been searching for a solution now for coming on to 50 years. Who knows?
You've mentioned a couple of minutes earlier algorithms and artificial intelligence, and I want to ask you, I mean, it is the central tenet of the field of cognitive science that the mind works in algorithmic ways. So do you think that investigating efficient algorithms or computational complexity more generally can shed any light on artificial general intelligence?
Yeah, so this is where I'm getting out of my depth here. I'm not at all a cognitive science expert. I don't really understand how the brain works. If I did, I'd probably act less stupid sometimes. What I do know is that the little bit of work I've tried to do in something that relates to AI, this is a long time ago, I was trying to do optical character recognition. And the approach that I took was very different from how the brain works. And it's not like the approach I took worked all that well. This was in the early 1980s, and I didn't know anything about AI or artificial intelligence at the time, or OCR, I should say. Um, does the brain work algorithmically? I don't know. I don't know. I do think that if we want to model real intelligence, it's not clear to me that algorithms are going to be the way to go unless you expand algorithms to include things like, deep neural nets, which, I mean, a lot of this is statistical, right? Indeed, look, a lot of intelligence is not deterministic. One of the things I discovered doing OCR is that you can show 100 people the same image and ask them, what character is this? And 60 of them are going to say one thing and 40 are going to say another. For example, with the company I worked at, they had to have special processing to determine B's, capital B's from eights and fives from S's, right? And I could come up with an image where if I show you this image and I say, is this a B or an eight? 60% of the people are going to say it's a B, 40% is going to say it's an eight. So what's the right answer? Is there an answer to this, right? Not all AI questions are answerable in any deterministic way. So if we're trying to model intelligence, then we have to be willing to accept that there's not always an answer and that there's some statistics involved.
Right, but what if we don't really want to model how we think? I mean, a famous example that I have in mind is, I guess you heard about John Searle's reply to the Turing test with his famous Chinese room argument. I mean, he posits a machine that would manage to pass the Turing test, but the inner workings of that machine do not take into account any computational complexity at all. I mean, his machine is so unfeasible that it cannot be built, even though he tries to disprove Turing's practical test for intelligence. So I'm wondering whether if we focus on very efficient ways of doing things and trying to design algorithms that work very smoothly, we might, even though our brain, our biological brain might not really work algorithmically, but at least we might devise a machine that manages to pass the Turing test, regardless of that, whether that counts as intelligence or not.
Yeah, so there have been attempts to really encode intelligence, right? So Doug Linnett's work a few years ago, just trying to encode everything that we know. And it's just such a daunting task. I don't know what the outcome of the work was, but I haven't heard much about it lately. So I assume it didn't really achieve what it was supposed to achieve. Back in the 80s, the big thing was expert systems, where you were just looking at a very limited domain and trying to make a system that could assist you with that. I remember there was one for locomotive repair called CATS, very limited domain. So I suppose if you're looking at a limited enough domain, sure, you can probably do it. But to have something that could really emulate human intelligence, I just don't know if we're going to get there without, with anything deterministic. I just don't know.
And coming back to algorithms, do you think that advances in the fields, in fields such as deep learning, will make the study of classical algorithms obsolete?
I doubt it. I doubt that classical algorithms will become obsolete because they still have great use. And, for example, if I am trying to find the best driving route from A to B, why use deep learning when you can use Dijkstra's algorithm and get the answer in a couple of seconds, if that, right? You don't need deep learning for that. If you're trying to do speech recognition, right? Why use deep learning to actually turn the sound into something that you can analyze when you can use a Fourier transform? So it's not clear to me that deep learning would replace everything. It can replace some things, but there's plenty of call for classical algorithms. Plus, remember, again, deep learning, this is all statistical based, right? So you don't necessarily get the best answer. You get some answer that's pretty good, but you don't necessarily get the answer that is the one that you really wanted.
Yeah, I mean, I was wondering whether you feel that at some point in the future we might be satisfied with a very good predictive black box instead of something that guarantees your result.
Well, certainly in some cases you have to accept that, like for NP-complete problems, right? So, if you want to determine the best route for a UPS truck to make its deliveries, you're going to wait a while, right? So, just I give this very simple example of, let's say a truck is going to make 20 deliveries. So there's 20 factorial different orders that it could choose to drop off the packages. And if UPS could determine 1 trillion orders per second, how long would it take to do 20 factorial? And the answer is about a month. So yeah, we have to be satisfied with an approximate solution for that. Another thing I want to talk about though with neural nets is the training. And the thing with the training is this is where bias gets introduced. And of course, this has been a big topic lately where, for example, there are programs that are being used for sentencing guidelines. And these have been found to be incredibly biased. Now, it's not that the algorithm is biased necessarily, it's that the data that you're using to train the algorithm is biased. So we really have to be careful about this. If we're using neural nets, it's very easy to bias them with your training data. And how do you guard against that? Again, this is not my area, so I can't really say much about it. But I do understand that we really have to be careful about these things.
But even though it's not your area, do you have any input on what we should do about this problem of bias in algorithmic bias?
No, I do not, because it really isn't my area, and I'd just be talking out of my hat if I said anything more.
I don't know how many people know this, but about 7 years ago, correct me if I'm wrong, you published another algorithmic book, namely Algorithms Unlocked. Can you please tell me briefly the story of that? I mean, you already wrote the Bible.
Right. So Algorithms Unlocked came about because our editor at MIT Press at the time, Ada Brunstein, contacted me and said that MIT Press was starting a new series of books that they called Essential Knowledge. And these would be small books, and by small, among other things, the trim size, in other words, the actual footprint of the book would be small. And she asked me if I would write one on algorithms. So I agreed to do that. And I sent her chapter 1, and they liked it. I sent chapter 2. They liked it a little less. I sent chapter 3, and they said, we need to talk. Because as I wrote, it got more technical, right? How do you explain algorithms in a good way without being technical? Now, there are books that do this. There's a wonderful book called 9 Algorithms That Changed the Future that is pretty not technical. I was not capable of doing it that way. I had to have some math in the book. So by then we had a new editor, Jim DeWolf. Ada had left. And Jim said, well, the editorial board at MIT Press, they're not really thrilled with this being part of the Essential Knowledge series. But we'd like you to continue writing the book, because I was ready to just bag it at that point. All right, I wrote 3 chapters, fun was had, and we're done. But Jim said, no, why don't you just write the book you want to write? And that will free you from the constraints of the trim size, because they were looking at really small trim size. And it's hard to get math on a very short line. So we went with a slightly larger trim size. I wrote the book I wanted to write. I tried to limit the math. I didn't go into data structures except a tiny, tiny bit, but very little on data structures. I tried to keep it just really algorithmic. The pseudocode looks more like numbered and lettered lists, so it doesn't look like code as much. And there were a few areas where I put in material that was not in CLRS. For example, I put in something on data compression. So I had to learn LZW compression to do this. I enjoyed writing it. I missed having my co-authors because getting back to the craziness thing, how you can get crazy. I got to read something out of the book here.
Sure.
So Julie Sussman, the world's greatest copy editor, copy edited this book. And I had written a chapter on algorithms for directed acyclic graphs. And it started out with doing a topological sort. And my original draft just launched right into, here's what a topological sort of a directed acyclic graph is. I got this note back from Julie. Dear Mr. Cormen, authorities have apprehended an escaped chapter which has been found hiding in your book. We are unable to determine what book it has escaped from, but we cannot imagine how it could have been lodging in your book for these many months without your knowledge. So we have no option but to hold you responsible. We hope that you will take on the task of reforming this chapter and will give it an opportunity to become a productive citizen of your book. A report from the arresting officer, Julie Sussman, is appended. So what Julie was objecting to was that here I had this book that was intended for a non-technical audience, and I had just launched into this technical stuff. Point taken, point received. So the new version of this chapter starts out not with talking about directed acyclic graphs, but with talking about how I was a hockey goalie, which I was. And then I stopped being a hockey goalie. And then I was going to play again a little bit. And I had to remember how to put on the equipment.
Right.
Because a hockey goalie wears a lot of equipment and you have to put it on in a certain order and how to do that. And that's a good example of a topological sort. So that's how I recast the chapter. Julie liked it a lot better. So yeah, I got caught up in my own craziness. And fortunately, I had Julie there to check me on that. So yeah, I missed having my co-authors. I did enjoy writing the book. And one thing that I was very happy about was that literally the day before it was going to press, I was able to add something. It went to press in early 2013, and my mother had passed away in December of 2012. And I wanted to add just, in loving memory note. And because I got to MIT Press the day before the book went to press, we were able to add that note.
I'm glad it worked out.
Yeah.
So you said that this book was written with a non-expert audience in mind. What do you think the average non-technical person should know nowadays about algorithms?
Oh boy. I would say the average non-technical person should just understand where algorithms fit in their lives. I don't think they should know much about any particular algorithm. I mean, what good is it going to do you to know how a Fourier transform works? You don't really need to know that in order to use a Fourier transform. But I think it's important to understand how algorithms fit into your life, and in particular, where we're seeing things like biases coming up in algorithms that can affect your life, and also understand the limitations of algorithms. A good example there is self-driving cars. So self-driving cars, they seem to be working quite well in almost every circumstance for which they have been tested, right? There was this case, of course, where the self-driving car did not work well and it killed somebody because it didn't see it didn't interpret what it was seeing correctly. But of course, the self-driving cars are mostly being tested in the Bay Area, where the roads are well marked. The roads are paved, in fact, and well marked, and it doesn't snow. I live in rural New Hampshire. Our roads have snow. They're not well marked because the snow plows scrape off the markings. And in fact, a lot of our roads aren't paved. So would I rely on a self-driving car to take me down a dirt road in the winter? Oh, and I should add, by the way, that a lot of the maps are inaccurate. So when I am looking at the map on my car's console, it's wrong. It's missing roads that are there, and it has roads that aren't. So would I rely on a self-driving car to take me around in New Hampshire in the winter? Not for a long time. And I'm afraid that I will become too old to drive myself before I would trust a self-driving car around here.
What would be your prediction regarding a time where you feel this would be safe to do, to drive a
Yeah,
self-driving car?
I really don't know. I really don't know. I feel like the mapping would have to get a lot better, and certainly the visual recognition. And just think about a snow-covered road. It's white everywhere. People have enough trouble picking up where the road is when it's covered with snow. So relying on a computer to do it, yeah, I don't know. I don't know. And another thing I should add is not only do we have snow, but we have ice. And for a self-driving car to detect that ice is coming and to react appropriately when ice occurs, it's very possible that it might react better than a person does when it hits ice. But of course, it would have to detect that it's hit the ice in the first place.
All right. So you mentioned when you discussed CLRS that you are taking one of the chapters out. I guess you didn't foresee that it wouldn't be so used. But I was wondering, when you initially wrote the book, was there any chapter that you didn't expect to be so popular and well used, and it turned out to be essential to algorithmic practice all over the place?
Boy, I don't think of anything like that. When every chapter we put in because we thought people would want to use it. We also know that no course can cover the whole book, and that's why we have the selected topics section where instructors can pick and choose, or people can just use the book as a reference. So, how many algorithms courses teach fast Fourier transform? Probably very few, but it's an important algorithm that we felt like people might want to refer to. I should mention that the chapter that we took out is not the only chapter we took out. Excuse me. We also took out various sections that we find people don't use.
Right. And for my last question, I mean, you said you wrote that during your PhD years, and you finished your PhD only 2 years after. Do you have any advice for students that are in graduate school and are doing their PhD at the moment, like I am right now?
Okay. So of course, the first thing is don't write a book because that will just delay you, right? It took me 8 years to get my PhD, and 3.5 of that were the book. And then the other thing that slowed me down was being a hockey goalie, because I was playing during the season probably about 5 games a week, sometimes 2 games at 2 different rinks in the same night. And when you're a goalie, that's a big commitment. Putting on, taking off the equipment, lugging it around. So yeah, don't get caught in a book writing project. That will just delay you. I happen to be very, very lucky that it was the right book at the right time and that I had really, really good co-authors. The one piece of advice I give to really all PhD students is something I wish I had been told at the beginning, which was, Cormen, for what will turn out to be the next 8 years, your goal is to identify 3 and even better 4 people who will be able to write strong recommendation letters for you when you finish. Recommendation letters that know you, know your work, and will say good things about you. Because I did not cultivate such letter writers. And when I finished, I actually had trouble finding appropriate letter writers. The work I was doing, it was on the book. That was my main thing. And my research was on a topic that nobody else at MIT was working on. And I wasn't really in touch with the other people working in this area. It was algorithms for parallel I/O systems. So when I graduated, I didn't really have a good set of letter writers. In fact, I was trying to figure out, who would be a good letter writer, and Charles Leiserson recommended Julie Sussman, our copy editor. So I'd worked with Julie when we were preparing the instructor's manual for the first edition of our book. And Julie got to know me pretty well and know my technical capabilities. So I asked Julie if she would write a letter, and she said okay. Then she called me back an hour later. And Julie's husband is Jerry Sussman, from Abelson and Sussman, famous MIT professor. And Julie said, Jerry said to me, who the hell are you to write a letter? She wasn't a PhD. She wasn't really in academia. So I really had trouble finding appropriate letter writers. So the advice I have for all PhD students is go in there thinking about cultivating letter writers. And in fact, I give this advice to undergraduates as well. You're going to need recommendations for things. It might be if you're trying to apply to grad school, but it might also be for a job. And you should be cultivating recommenders. So that is the advice I have for especially PhD students, but really for any students at any university.
And what about people that are still in high school and they are wondering whether computer science is for them or not?
Well, it might not be the thing that they study, but they should know something about it. At Dartmouth, we have an event on move-in day, the day that all the first-year students, what are called freshmen at other places, the day that they move in. And we have it in our big field house. There are tables set up for various offices at Dartmouth, including some of the academic departments. And I've been going to this thing for years. So I'm at our table, and people are circulating through. And any student that makes eye contact with me, I go out and chat them up. And the first thing I say is, are you interested in computer science? And of course, a few of them say yes. And I start telling them about our courses and how to get started. Of course, the majority say no. And then I say, well, what are you interested in? And they tell me. And 90% of the time, my response is, oh, then you are interested in computer science. Because it's in everything. At Dartmouth, we have a lot of students who want to do economics. We have a great economics department, fantastic econ department. So a lot of students want to do econ. Plus, we don't have a business major, so that's the closest thing they can find. Well, how are you going to do economics without computers? Right? You should know something about computer programming.
Right.
And really almost anything. If they're interested in studio art, they should know about computing because they can do digital art. In fact, in our own department, we have a digital arts minor. So really, maybe if you're interested in 18th century French literature, computer science won't be as relevant, although you might want to do textual analysis. So for almost anything that the students tell me they're interested in, you do need to know some computer science. So that's what I would say. For almost any high school student, there's a computer science connection.
Great. Professor Cormen, thank you for your time. It was an honor being able to talk to you.
Well, it's been a lot of fun, Teddy, and I wish you the best.
Thanks. Have a nice day.
Okay, bye-bye.
Bye.